Well, this is split into several different parts in your book, 3.1, 3.2 through 3. They're all part of the same thing. So I'm actually going to talk about 3.3, graphical solutions of applied problems, and I'm going to mention as I go through each of the pieces of this why we're doing each of those pieces. I think it gives you a better complete picture. You're still going to go through the homework in each of the different sections, but let's let you see why you're trying to do this. So first of all, even though there's no good reason at the moment, let me just talk about a theorem. If a linear programming problem has a solution, then that solution must occur at a vertex of the feasible set S associated with the problem. Like all theorems, this is very formal, very strict. Math theorems are all about being very precise and saying exactly what we mean, no more, no less. You want to get as much out of a theorem as you can, but you don't dare say anything that's not true. So they're worded very cautiously. If a linear programming problem has a solution, we've been dealing with linear equations, so if there's a solution, an optimal solution is what we're going to call it, then that solution has to occur at a vertex. That means if I graph it out on an xy axis, I'm talking about a corner point. Rephrase that, I mean this is in your book, but rephrasing that, the max or min solutions have to be on a corner. So the technique is this: test all the corners. Plug every single corner point that we've got into our equation that we're trying to find a maximum or minimum for. The highest one is the max, the lowest is the min, and we're done. As a side note, if I have two corners that are right next to each other on the graph, I'm going around the shape of the graph, and I'm going to talk about what a solution set is in a second, but if I'm going around the edge of the graph and I find two corners, and both give the same answer, that's the best answer, the maximized answer, the minimized answer, then all the points on that line segment between those two edges are going to be the same optimal answer. And that's nice because it means there's different ways to get the maximum profit. There's not just one right answer, there's several. And you'll find this a lot in some companies. There's like a profit line, and you're able to sort of ride this, and you can do some different things. And the best part is, the more you have in terms of maneuverability, the more you're able to interact better with people who might have been competitors, but actually it turns out you can both interact well, and you can come up with industrial alliances and the like. So here's my example. I think I'm going to do one or two examples of this. Again, I'm doing it from the, let's start with the word problem, and we're going to get this to some points that look a little bit more like maybe parts of the earlier sections of Chapter 3. So I have a children's store that sells both a large avian and a Tickle Me Selgo plush doll. No copyright infringement intended. The profit for a large avian is $1, while a Tickle Me Selgo brings in $2 of profit. The manager only has shelf space for 4 dolls total, and her contract with Poppy Seed Lane, and we wonder how to get there, requires, to keep scarcity of the more popular Selgo intact, that for any 5 dolls she purchases from them, and that's the most she can, she has to get rid of double the number of large avians. So if she buys a large avian doll, then it's going to have to be 5 minus 2, because we're getting rid of 1. So the first thing we always do with the word problem is try to set up the equation system. And if you go through the chapter in sort of the way the book does through the examples, the format is this. We always talk about maximizing or minimizing. Here, because we're discussing profit, it's going to be maximizing. We want to make profit as best as possible. So I'm going to have a maximize equation. We're going to call it capital P for profit. And here's the rule. Profit is this. It's $1 for the large avian. I'll call large avian A. And it's $2 for the Tickle Me Selgo. So P equals A plus 2S. If I plug in the number of avian dolls I sell and the number of Selgo dolls I sell and add them together like this with this $2 multiplier here, that will tell me my profit that I bring in for them. Then we have this subject to business. And it's this subject to that we're going to talk about next. The subject to is going to have some deals. For all of these problems of this nature, I have to purchase a positive number of avian dolls. I can't buy negative dolls. Same thing for the Selgo. So there will always be this bottom part here. We'll talk about this as being non-negative, because 0 is not exactly a positive number. It's kind of, well, half exactly in between positives and negatives. So we call these non-negatives, and this is called non-negative variables. My variables in this setup I'm doing are a and s. It could be x and y too, just as well. So these are non-negative variables. And a lot of the conditions we're going to break on into in the next chapter are going to require that our variables be non-negative. This is kind of automatic here. We almost always have this. So that's our first thing to observe. And there's nothing in the word problem that tells me this other than common sense. I couldn't buy -5 avians. I couldn't buy -2 Celigos or anything like that. Then we have some additional restrictions, and this is going to be where inequalities come into play. And so the first part of this chapter talks about graphing them, and that's what we're going to do in a second. But first I have to cook them up from the problem. So let's look. Only has shelf space for 4 dolls total. So however many avians I have plus however many Celigos has to be less than or equal to 4. I don't have to fill up my shelf all the way. Turns out in this one I will, but I don't have to. 4 dolls total. At most 4 dolls. So I do this less than or equal to. Convince yourself with this equation that it's legitimate. And then there's this other thing. We're going to kind of work it out here on the side. To keep the Celigos popularity intact, for every 5 dolls, the 5 dolls that she purchases from the Poppy Seed Lane, we have to take off double the number of large avians. If I solve this equation around by adding 2a to both sides of this, this tells me that 2a plus s is less than or equal to 5. So now I have my two equations that I'm restricting myself on. These are the ones that we're going to graph in just a second. And you might remember graphing inequalities from a college algebra class, but don't worry, I'll go through it. This two equations here that we graph, combined with these, which tell us I'm going to be in quadrant 1 of my graph, is part of what we call the solution set. And so when it talks up here in the theorem about a feasible set S, that's going to come from these things right here. All right. So part 1 of this section, I've got maximize this subject to these constraints. And these are non-negative variables section. So let's graph this guy. I guess I don't really have x and y so much as a and s, but you get the idea. Here's what we're going to do. I'm going to solve each of these two into slope-intercept form. So s is less than or equal to minus a plus 4, and s is less than or equal to minus 2a plus 5. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay. This guy gets to be this color. So my y-intercept is up here at 4. And if I plug in 0 for s, I get 0. It's less than or equal to minus a plus 4. Minus 4 is less than or equal to minus a. 4 is less than or equal to a. So I know that my x-intercept, which we're calling our a-intercept, is here. I connect these two lines like this. Because I'm talking about this less than or equal to point, I have to plug in a test point to see what side of this line I'm shading. It's a solid line instead of a dashed line because it is less than or equal to. There is that equal part there. I can plug in test points. When in doubt, plug in the test point 0, 0. If I plug in 0 here and 0 here, I get the true statement that 0 is less than or equal to 4, which is true, so I know I'm shading this side of my graph. I'm going to do that shading very, very lightly. I'm about to get a more specific piece of information out of it. Next, I talk about this one. Now I've got the y-intercept at 5. And then if I plug in 0 for s, let me just do that little calculation here. 0 is less than or equal to minus 2a plus 5. Subtract 5 off both sides. Divide both sides by negative 2. This is just some algebra. 5 halves is going to be bigger than or equal to a. And I know where the point 5 halves is. It's right here. So I've got my second line, like so. Again, it's a solid line because it's a less than or equal to here. And again, if I plug in the test point 0, 0 back into the original equation here, 0 is less than or equal to 5 is a true statement, so I know I'm shading this lower part here. Lastly, I've got these two pieces of information. A is bigger than 0, S is bigger than 0. That tells me that my final actual solution area, now let me erase some of these dashes so we can see it as clearly as possible. All of my y's have to be positive, that's all my s's. All of my x's have to be positive, that's all my a's. I have to be below each of these lines, so here I'm below the one line, and now over here this is the smaller one, so I follow it. This place that I'm highlighting in has a special name. Alright, not the most awesome highlighter in the world, but that'll have to do. This place right here has a special name, and that name is capital S, and this is the feasible solution set that they talked about right here in the theorem. So now I have my feasible solution set, and here's what the theorem says. The solution must occur on a vertex of that feasible solution set. So let's look at my vertexes. I've got a vertex right here. We'll call this point capital A. I've got a vertex right here. We'll call this point capital B. Where these two lines cross, I've got another vertex. We'll call this capital C. And lastly, right here, I have one more vertex. All the points, all the corners of my lines that are next to this highlighted in area, we'll call this one D. So let me get some coordinates for each of these. I have A, B, C, and D. A is super easy. That's the origin, 0, 0. B the same way. The x is 0 for B, and the y is up there at 4. For C, that's where these two lines cross. I'm going to have to do some algebra to figure that out. But for D, it's right here. We knew what that was. That was the point 2.5. So I have 2.5 for my x and 0 for my y value. Alright, we have to talk about what C's coordinate point is. I have to figure out what that position is. And so I go back to my equations. I've got 2a plus s equals 5. For solving this in terms of the addition method that we talked about before, I could also notice just as well use the Gauss-Jordan process of elimination, but I'm just going to use addition because that's going to be easy. A plus s equals 4. I'm going to just put equals here as well because I don't want to mess around with the less than or equals to. This is happening on the line, so it's happening on the equals part. I'm going to use the addition method and just subtract the bottom line off the top. So I have 5 minus 4 is 1, s minus s is 0 s's, and 2a minus a gives me a single a. So a equals 1. I take this and plug it back into one of these equations. 1 plus s equals 4. That tells me s equals 3. So now I know my coordinate points for C. It's at the point 1, 3. And I'm almost a good enough artist you could have gotten that off the graph. Not quite. My a-axis is a little bit funky. Now that I have these 4 points, I take them, so these points right here are the corners that the theorem talked about. These are the vertex corners. The vertex corners of my feasible set S. Now I have to plug them into my equation. This equation I'm trying to maximize because it's profit. That's just common sense. And here's my profit equation. P equals A plus 2S. P equals A plus 2S. If A is 0 and S is 0, I get out 0 for my profit. If she buys no dolls of any sort in her store, she's going to make no profit for that item, which makes sense. If I plug in 0 for A, plus 2 times 4, because I'm doing 4 of the Tickle Me Selgos, this gives me a profit of $8. If I do 1 large avian plus 2 times 3 Tickle Me Selgos, that gives me a profit of $7. And finally, if I was to somehow be able to pull off 2.5 large avians plus no Tickle Me Selgos, that would just equal 2.5. Notice this last one right here doesn't really work in the real world. It's not possible to actually pull that off. That's okay. Sometimes when you set up a coordinate system and you set up a model for a word problem, you get things that aren't true. You'd probably end up trying to round to the nearest one. So you would try, just 2 tickle me Selgos, and then you wouldn't be able to get any, 2 tickle me 2 avians, and you wouldn't be able to get any Selgos. But we're trying to maximize. We don't care about all the answers. We just care about the solution. The biggest one is this one, which means the answer is B, which means the best thing the store owner can do is to buy 4. She only is allowed 4 because that's all the shelf space she has. Buy 4 Selgos. And no large avians. So that's her answer, that's her optimal situation. And if we looked at the problem, we kind of suspected that. Tickle me Selgos bring more profit, so she should buy as much of them as she can. This line right here is her shelf space. As long as it was possible for her to fill up her shelf space, all 4 of her shelf space spots with the higher profit item, that clearly was her best choice. This red line was a crazy condition imposed by Poppy Seed Lane on her in terms of their sales distributions, and that did affect something. She would not have been able to fill up all of her shelf space with the avians. That was never going to be possible for her because of her restrictions that were going on. But that's okay, because the avians weren't the popular item. They weren't the ones that had the most profit for her. So she was able to hit that better point right here. This is how you tackle these types of problems. The earlier sections of the chapter just talk about graphing these. The later sections of the chapter just talk about cooking up from a word problem these equations. But the idea is to put it all together, get these points, plug them back into the profit or the cost equation, and find the max in this case, or the min if you're doing a cost equation, and get that answer. Before I quit this example, let me point out some problems with this process. It's brilliant. We've got a theorem. We know how to graph things. We're able to cook up equations from word problems and graph those equations, and we're able to take that graph information and get a final answer. $8 is our maximum profit. $8 is max profit. But we've got a problem. I can only cope with things where there's 2, because I can only graph 2 things. I could maybe try to do a 3D graph if I wanted to, have an X, Y, and Z, but anytime I have more than 2 or 3 things, this process isn't going to work because I can't graph it. And if I can't graph it, I'm going to have trouble figuring out where all these points are that I'm supposed to find. So the next chapter is going to help us with this. We're going to do a couple more things this way. Sometimes this is the original way, this is the gold standard, and this helps you get a good picture in your mind of what you're trying to do. But just keep in mind there's some limits to this process. It's got some unfortunate parts, so we're going to have to learn to do something a little bit more advanced and clever, because we might have a store that sells more than just 2 toys. You know, some stores sell like 3 or maybe even 5. Okay, so this is what we got. This is how you do it. Go through this example and look at it, and then I'm going to give another one right after this that you can click on that will talk about how to solve a minimization problem.